Hi, everyone. My name is Christian Mullard. I'm the head of marketing with Data. Welcome to this webinar. We have about 250 registrants today, so thank you. The webinar will last about an hour, followed by Q&A. So over the course of the webinar, please feel free to ask any question that you may have anytime, and we'll be addressing those at the end of the webinar. Our speakers today are Geraldine Dufour, who is a senior analyst at Data. Hello, Geraldine.
Hello, everybody.
And also we have Quentin Kinney, who is the manager of our research department. Hi, Quentin.
Hello, everyone.
So to start with a few words about Data, can you go to the next slide, please? Thank you. So in short, we're a spin-off of a research center. We've been independent since 1991. It's been a while. We're about 70 people, based mostly at the HQ in the French Alps. We also have an office in Singapore to address the Asian markets. So our teams consist of economists, analysts, consultants, also modeling specialists, data scientists, and developers, in terms of the online interfaces. We have clients all across the globe, mostly policy makers and strategists. While we've been growing over and over from year to year. Our core expertise lies in the statistics, of course, and the modeling. We've developed a range of models. Also the research and intelligence to scrutinize the markets, and last but not least, the expertise in terms of energy and climate issues, and lately also clean technologies, H2, BESS, CCUS, you name it. Next slide, please. So speakers have already been presented. So next slide, please. So there's going to be three parts for this webinar. Part one is the analysis of key energy and climate figures for 2023. So basically, we're going to take a look at the consolidated statistics. It's very important. It's not estimates. We're not talking about estimates. We're talking about the actual statistics that we've been gathering from our sources and processed. So this is sound and reliable information. Then second step, we're going to drill down into the energy types, and especially the demand side. And then the third part is the COP28 pledges and, analyzing to which extent those are achievable or not, and especially looking at the 2030 milestone, which is quite important because, well, basically 2030 is tomorrow. Okay, so enjoy. So Geraldine and Quentin, you have the floor.
Yeah, thank you, Kristen. So let's start with the analysis for last year. So next slide, please. So in three figures, so let's have a look at three main indicators for 2023. So first, economic growth. So in 2023, the G20 GDP grew by 3% in line with the last year and the pre-COVID crisis period. So in this analysis, we will focus on the 2010-2019 period, and we will not take into account 2020 and 2021 due to the sharp drop and the rebound, so to analyze normal periods. So economic growth returned to its historical trend of 3% per year. It was the main driver for energy consumption, which grew by 2.3% in 2023. This is slower than economic growth, so there is a kind of small decoupling between economic growth and energy consumption, but still energy consumption grew at a fast rate, much faster than over the historical period. So this increase in energy consumption had a strong impact on CO2 emissions, which continued to increase last year by 1.7%. This is a steady growth, and this is faster than over the historical period. So first, let's have a look at the GDP growth in 2023. So as I said, the GDP returned to its normal average growth of 3% per year, but there is a strong gap between the trends in non-OECD countries, especially China, India, Indonesia, and OECD countries, where the GDP grew, but was at a slower rate. So non-OECD countries, they account for 48% of the G20 GDP, and China among them for half of it. So China is about 1/4 of the G20 GDP, and it was really a driver for economic growth in 2023. So the 5% increase in GDP in China was led by the end of the zero COVID policy in early January. So it had a tremendous impact on economic growth, on consumer demand, on industrial activity. It's still below the 7% per year growth over the historical period, but still it's a very dynamic growth. The growth was also steady in India and Indonesia, spurred by public investments. Both countries are emerging and have a very fast growth rate over the last 10 years, but it was also a pre-electoral year, which contributed to fuel public investments. Economic growth was also steady in Russia. It was a rebound year after the international sanctions in 2022. So in Russia, the military spendings and fiscal policy contributed to this rebound. Well, in the non-OECD countries, the GDP growth was very steady. On the contrary, in OECD countries, it was slower, especially in the EU, where even Germany posted a small decrease due to the geopolitical uncertainties, to high inflation, high interest rates. So the economic was not that, was very, very slow. In the United States, on the contrary, the economy grew at an average rate of 2.5% per year over steady consumer spending. In Japan and Korea, it was a third year of growth, but still with weak economic demand. So we have very contrasted growth trends between OECD and non-OECD. And we will see it in energy consumption too. It's the same. So the energy consumption rose at a steady pace of 2.3% per year. This is faster than in 2022 and faster than the average rate over the historical period. So the energy consumption was spurred by China, India, and Indonesia. China alone accounts for 1/3 of the G20 energy consumption, and the 2023 growth was very steady at around 7%. So we saw it was due to the economic growth in those countries, but also to temperatures effect that contributed to rise energy consumption in China and India. On the other hand, energy consumption was declining again in OECD countries. So it remained stable in the United States. In the United States, it was there was a sharp contrast between energies. For example, the US oil consumption grew in 2023, but electricity consumption declined due to milder temperatures. So overall, the energy consumption in the US was stable. In the EU, in Japan, in Korea, there was a small increase in industrial activity, but not very fast. So that limited industrial energy consumption, and milder temperatures too, and also higher renewable and nuclear power generation contributed to limit energy consumption in these countries. So the drivers for energy consumption is really the non-OECD countries. So next slide. Thank you. So where energy intensity is concerned, there were few energy intensity improvements in 2023, with a strong decoupling between OECD countries on the one side and non-OECD countries on the other side. So in OECD countries, there was a higher renewable power generation that limited energy consumption for fossil consumption, weak industrial activities. So the energy intensity declined again and faster than the historical trend. On the other hand, in non-OECD countries, it was a second year of stagnation because it slightly increased in 2023, declined the year before. So this is bad news. There is no improvement in non-OECD countries. And if you look at the G20 overall, you see that the average since the COP21, since 1915, is not sufficient to meet the 2-degree target. So we need to focus on energy intensity, on energy efficiency improvement to meet the targets. So that's the same for CO2 emissions. There was a new increase in 23, spurred by China and by India. So if you look at these two countries, they account for nearly half of the G20 emissions, China for almost 40% and India for 10%. So they have a strong weight in CO2 emissions. And in these countries, CO2 emissions increase dramatically because they have very CO2 intensive energy mixes and power mix. So anytime they increase their energy consumption, it's an increase in fossil fuel consumption and in emissions. So on top of this increase in CO2 intensive countries, there were also additional impacts of lower hydropower generation in China, in India, and also the impact of the global air transport and road transport recovery in China. So all these factors contributed to raise CO2 emissions. Well, there were also a touch of hope because there was a new decrease in OECD countries with strong falls in the EU and Japan. But still, we should be reducing CO2 emissions by almost 6% per year to reach the 2-degree pathway, and CO2 emissions are still increasing, so that's very bad news. So this is partly due to a stable carbon factor, because the G20 energy mix is still very CO2 intensive. If you see the two graphs, what is done, what is achieved, and what should be done to achieve the 2-degree target. And we are very far from this trend. So this is due to the share of fossil fuel in the energy mix, which remain very strong, and the decarbonisation, which is progressing slowly in OECD countries, but stalling in emerging countries. So we will see more details for energy efficiency and CO2 emissions and renewables in the second part. So what to remember for the global trends? 2023 was a return to normal economic growth and to a rising energy consumption, which increased faster than its historical rate. Energy consumption continued to increase, so there is no real decoupling between economic growth and energy consumption. And the rate of reduction in energy intensity is still incompatible, is still insufficient to meet the 2-degree pathway. So this trend is strongly differentiated between countries, between emerging countries on the one hand and developed countries, OECD on the other hand, depending on the evolution of their energy mix and the structure of their production, of their GDP. So this contributed to new increase in CO2 emissions, despite a rising renewable wind and solar generation. Their share in the energy and in the power mix only increased marginally. So we have to reduce the carbon factor to achieve temperature rise objective of 2 degrees and to limit the growth in CO2 emissions. So now let's have a look on the trends by energy.
Thanks, Geraldine. Sorry to interrupt. Just a reminder to everyone. If any question pops up, anytime, please use the Q&A chat box of Zoom, on the bar at the bottom, and we'll be answering those questions at the end. Thanks. Go ahead, Geraldine. Sorry.
Thank you. So in one slide, all the figures you need to know for the trends in 2023. So as I said, a return to a normal economic growth of 3% per year, energy consumption rising by more than 2% in 2023, which is faster than the historical rate. So all energies were on an upward trend. For example, coal consumption, it increased by 2.5% in 2023, which is much faster than the historical trend of 0.5% per year. So coal now accounts for 1/3 of the G20 primary energy consumption, which is huge, and its share is rising since 2010. Oil consumption also increased dramatically by 2.6% in 2023. So this is much faster than over the historical period, and this is really bound to the to the resumption in global air traffic and in road traffic in China after the end of COVID restrictions. Where gas is concerned, gas increased slightly by less than 1% in 2023, after a small decline in 2022, which was due to very high gas prices, to the global energy crisis, and gas consumption is rebounding, though at a slower rate than over the historical period. And electricity consumption continued to increase at its average rate of 2.5% per year. So where coal is concerned, we can see that coal consumption continued to rise by 2.5%, especially in non-OECD countries, which now account for 85% of coal consumption. So if you see the second graph, the primary coal consumption, you can see that since 2000, the increase in coal consumption has been led by non-OECD countries, especially China, which accounts for more than 60% of the G20 coal consumption, India with 14%, and Indonesia. So these three countries together account for nearly 80% of the G20 coal consumption. So these three countries, we said, had a very steady economic growth last year, which translated into a higher energy demand. And since their energy mixes are very coal intensive, it translated into an increase in coal consumption by 6% in China, 8% in India, and 14% in Indonesia. So here we make a focus on Indonesia because it's only 3% of the G20 coal consumption, but it's increasing at a very fast rate, above 10% per year since 2010, because Indonesia is a major nickel producer. Its nickel production has more than doubled in 3 years, so it requires higher amount of coal to refine, and it's raising Indonesia's coal consumption. So these three countries were the main driver for coal consumption and CO2 emissions in the G20 in 2023. On the other hand, coal consumption continued to decrease in OECD countries, especially in the US, where it fell by 16%. So this is due to the continuous coal to gas switch in the US power sector, where gas-fired power plants are increasingly replacing coal-fired power plants. In the EU also, there was a slight increase or stability in coal consumption last year or in 2022. So now it's a return to normal trends with a 23% fall. In the EU, as in Japan and South Korea, the lower coal consumption in the power sector was also due to an improved nuclear power generation and higher renewable power generation in Australia too. So we can say that there is very differing or diverging trends between OECD countries, which are very coal-consuming, and OECD countries. So oil consumption grew by nearly 3% in 2023. As well as for coal, most of the increase is due to non-OECD countries, as you can see on the second graph, that the oil consumption in OECD countries is slightly declining. So it was due to a strong increase in China, where oil consumption grew by 11%. So that was due to the end of COVID-related restriction that spurred traffic. So road transport, air transport, the global air transport also. And in the US, there was also an increase in road traffic that contributed to raise oil consumption. This growth in China has made the country nearly on par with the US. So you see that the US now accounts for 23% of the G20 oil consumption, and China is 22%. So they are nearly on par, and certainly that next year China will overtake the US in terms of oil consumption. On the other hand, oil consumption declined in the EU and in Japan, so this contributed to tame the growth in oil consumption. So where gas is concerned, there was a slight rebound in gas consumption, but not as much as we could expect after the small decrease in 2022. So this is due to very high gas prices. So the strong rebound was mainly occurred in non-OECD countries, in China, in Russia, in India. India, for example, had a nearly 8% decrease in oil consumption in 2022 and a more than 10% increase in 2023 because India imports LNG with very high LNG prices last year or in 2022. So the slight decrease in 2023 contributed to spur LNG import in India. On the other hand, in the OECD, there was a second drop in a row, especially in the EU and Japan. In these two countries, the higher nuclear and renewable power generation reduced the need for gas in the power sector. In the US, there was an increase in the gas demand from the power sector because there were 9 gigawatts of new gas-fired capacity installed during the year. But on the other hand, milder temperature reduced the need for gas for heating in the residential and commercial sectors. So the growth was limited in the United States. So electricity consumption, in the next slide, thank you. It continued to increase in 2023, back to its average rate of 2.5% per year. The growth was very dynamic in non-OECD countries, especially China and India, around 7% per year, in line with the historical trends. It also increased in Brazil, for example, whereas in the OECD, including in the US, there was a slight decrease in electricity consumption. So in the US, the milder temperature reduced the need for air conditioning, for electricity, and then for electricity, whereas in the EU and in Japan, the slow economic growth contributed to reduce electricity consumption. So if you see the second graph with the share of electricity in final energy consumption, you see that it has been growing regularly since 2000, from 70% to 23%, sorry, in 2033. This is a regular growth, but it's not, it has been stagnating in the last years, so it's not sufficient to replace other fuels and to reach the 2-degree pathway. So how was this electricity produced? We can see that there was a new growth in thermal power generation. So thermal power generation from coal, oil, and gas continued to increase last year, though at a slower rate than renewables, but still increasing and accounting for around 60% of the G20 power mix. So we have 60% thermal, around 10% nuclear, 15% hydro, and 15% renewables. So there was a steady growth in renewable power generation, which accounted for 30% of the power mix, including 9% for wind and 6% for solar. So there was a strong increase in solar generation with 25% and 10% growth for wind power generation. Hydropower generation slightly declined by 3%, which is due to climate effects, with the climate effects of the climate change, the El Nino and its counterpart in Indian Ocean. So a lower hydropower generation that was offset by 2% increase in nuclear power generation in Europe, in Japan, in Korea. So let's focus on wind and solar for a touch of hope. So China and the EU, to a lesser extent, accounted for most of the increase in wind power generation in 2023. So if you see the second graph with the new capacity additions, we had a record in wind installation with more than 113 gigawatts installed in last year. So this is a rebound after the slight decline or the slowdown, at least, in 2022, and a new record compared to 2021. China accounted for most of these installations, for more than 60% of this installation, and China alone, with 76 gigawatts installed as much wind power in 23 as the entire world in 22. So China is really a giant in terms of wind installations and in terms of wind power generation. So wind power generation grew by 10% in the G20, with very strong growth in China, in the EU, in Brazil, and India too. And if you see the first graph, you can see that China accounts for 40% of the G20 wind power generation, with nearly 900 terawatt-hour of wind power generation. This is as much as the EU and the US together. So we have 40% China, 20% EU, 20% US, and 20% the rest of the G20. So China is really the giant for wind. And that's also the case for solar, because China, as for wind, installed as much as solar capacity in 23 than the entire world in 22. So there was really a surge in solar installations with nearly 350 gigawatts installed. China accounted for more than 60%, with more than 217 gigawatts installed. It was more than the entire world the year before. Installations were steady too in the EU with more than 50 gigawatts, in the US with 25 gigawatts, but still it's marginal compared to China. So this surge in installations contributed to a 25% increase in solar power generation in 23, with a 37% increase in China. So China accounts for 40% of the G20 solar power generation. This is as much as the EU, the US, and India together. So China is one of the largest coal consumers, the largest emitter, CO2 emitter, but also a giant in terms of wind and solar. So what to remember? We can remember that in 2023, energy consumption grew faster than before the crisis, particularly for coal and for oil. So the weight of fossil fuels in the G20 energy mix is almost not decreasing, especially for coal and oil, which is driven by non-OECD countries, especially China and India, and by the global transport sector and air transport. Only gas, which is the least CO2 emitting fossil fuel, is stagnating due to very high prices on LNG markets. What to remember is also that the trend gap is widening between OECDs and non-OECD countries, especially China, India, and Indonesia, which are really kingmakers. And a touch of hope to finish is that renewable power generation continues to increase rapidly, with record installation led by China, which accounted for 60% of global installations and installed as much renewables in wind and solar in 23 as the entire world in 22. So this contributed to increase wind power generation and solar power generation. But still, we need to make additional efforts to meet the 2-degree pathway. Thank you.
Thank you, Geraldine. Let me take it from here and wait. Yeah, here's my base. So now, so we've talked about at length about what happened in 2023 compared to 2022 and previous years. Now we're still going to look at historical trends, but put them into perspective with what came out mainly of the last COP, the COP28, which is the Global Renewables and Energy Efficiency Pledge. So specifically looking at are the objectives that have been issued realistic, and also are they sufficient? So we'll conclude hopefully on that at the end of this section. Real quick, let me remind you that the slides will be available and sent around tomorrow. So no need to ask because we've had several questions in the Q&A box regarding this specifically. You will have the slides around tomorrow. So first of all, what is the Global Renewables and Energy Efficiency Pledge? So as said, it's one of the main things that came out of the last COP. So 120 states committed to basically accelerate the pace at which renewable energy is deployed and to improve the pace at which energy efficiency improves. So concretely, what it meant was to try to triple the world's installed renewable capacity by 2030 to around 11,000 gigawatts or 11 terawatts, and to double the global average annual rate of energy efficiency. So we'll get to that. What does energy efficiency means on a global perspective? But the idea is that we are at around 2% per year over the last years, and we would like to get to 4% per year on average by 2030. So again, the idea is look at historical trends to see if this required indeed a major shift, which the energy efficiency objective is a shift by definition compared to historical trends, and also is this consistent with the objectives of the Paris Agreement. So let's look first at the objective to triple renewable capacity by 2030. So renewables have been developing quite fast, especially since 2010. So basically, renewable capacity has doubled, more than doubled since 2010, between 2010 and 2020. And it has even increased a little bit more at a higher rate since 2020. So we went from 8% per year on average between 2010 and 2020. And now, since 2020, we're at around 11% per year. So this would mean that, again, it's difficult to compare to 2.3 with the previous figures, but 2.3 relates to the objective to triple the capacity. So if we keep up with the pace that we've had since 2020, we would more than double the capacity between the COP28 and 2030, as opposed to triple the capacity, which would require an average of 16% per year growth for renewable capacity. So we're not on track yet, at least. So a lot of this has been, I think, brought up by Géraldine in her presentation, but let's look at how this renewable capacity and the development over the years has been, in different regions of the world. Like what we're seeing now is that emerging economies, and this is mostly driven by China, as this has been made obvious in the beginning of the webinar. So emerging countries, non-OECD countries, account for 58% of total installed capacity in 2023, as opposed to 42% for OECD countries. China has been on a huge base, which would be much higher than the ×3 if you look at China itself and you consider the pace at which they've installed a new renewable capacity. It goes way beyond the ×3 objective, but other countries are not on that pace yet. So yeah, another version of the punchline that Géraldine delivered earlier is that China installed more capacity than the rest of the world combined in 2023. It also installed, as Géraldine stated earlier, more capacity than the entire world combined, including China, in 2022. So this is quite impressive. In terms of, just to compare emerging and developed economies, in terms of shares of renewables, there's a bit of a convergence because of these dynamics. So 50% of the capacity in OECD countries is renewable based, and in non-OECD countries, it's a bit lower, but it's not that much lower. It's 44%. Now, let's have a look at operating capacity and projects, so capacity under construction and development. There is around 9 terawatts of capacity globally, power generation capacity globally. 45% of that is renewable-based. If you look at projects that are currently under construction from our power plant tracker database, we are at a very small majority of projects that are renewable based. So we go to 45% from operational projects to 53%. And then if you look at projects under development, so this is less advanced than under construction, obviously, but there are various stages of development that are included here, from announced projects to projects that have been authorized and that are very close to getting into construction. So if you look at these projects, we are at around 2/3 that are renewable based. What that means is that there is a shift towards renewables, but there's still a very significant capacity that is not renewable based. And we're talking about projects that are under construction and that are going to be commissioned or not, but that are going to last maybe 20, 30 years from now. So this is a bit worrying that the shift is not as obvious as it is. Now, let's again look at the project pipeline. So under construction projects and under development projects. So we were, at the time of the COP28, we were at around a little bit less than 4 terawatts of renewable projects. If we look at projects that have been commissioned since then, we're a little bit under 4 terawatts. If you take into account the projects that I've mentioned in the previous slide that are under construction and under development, knowing that this is a very strong assumption to consider those that, that they're going to be commissioned by 2030, because a lot of these projects, especially the under development projects, are not like the feasibility rates, the likelihood that they're going to be commissioned and that they're going to be commissioned before 2030 is not necessarily, it's definitely not 100%. I couldn't give you a figure, obviously, but it's lower than that. So this is already a very ambitious and optimistic assumption. But even if we were to consider all of these projects, which would basically increase the current capacity by 80%, we would still fall short by around 4 terawatts of the objective of 11 terawatts. Now, if you consider, this is pretty rough based on the current share of small-scale renewable projects, so basically rooftop PVs and other decentralized projects, which are not taken into account in the project pipeline. Obviously, the gap would be a little bit lower, but still, it's pretty, it's a real challenge. Now, before concluding and going to energy efficiency, let's put these capacity-based targets into a little bit of perspective. Basically, capacity has increased by a lot, from 24% in 2000 to 45% in 2023. The problem is that the real metric is generation or emissions. If this capacity target is basically an underlying target for a wider objective, which is to reduce emissions, right? So if you look at electricity generated by renewables in the same period, we actually went from 18% to 30%, right? Because the load factors on average are lower for renewable projects than they are for other non-renewables, such as thermal projects. So they produce less on average. And the real metric being emissions. If you look at the emissions, despite this very impressive development, if you look at accumulated emissions over that period, the increase in renewable has basically only reduced accumulated emissions by around 7%, which is significant, but it seems quite low compared to the scale at which renewables have been developing in terms of capacity. Again, if you look at the primary energy mix, we are at around 15% of the total energy mix in 2022 that is renewable based, which is only 3 percentage points above the 1990-2010 average. So what we're concluding here is that, well, the capacity target is not the best metric, and also that despite this increase in volume of capacity and even in generation, I mean, this has not really contributed to shifting the energy mix towards renewables significantly and to reduce CO2 emissions from energy significantly. So basically, renewables are not really replacing fossil fuels. They're merely adding up to them. Now, let's look at energy efficiency. So first of all, a disclaimer of what we mean by energy efficiency in that specific context. Usually, energy efficiency is basically relating to the ratio between the energy consumption for the energy that is consumed to produce a given output. So this output could be anything. It could be an industrial product, a energy service, for example, lighting or heating in a dwelling, or a distance traveled if you look at transportation, right? So we have a very specific activity and we can measure the energy consumed to get that specific output. But at a larger scale, we don't really have a clear notion of what is the relation between energy consumption and activity. And when we use GDP, the term energy intensity, I think, is more appropriate than energy efficiency. Energy intensity does, not only includes energy efficiency improvements and evolution over time, but also structural effects that changes basically the dynamics between activity and energy consumption. For example, a very typical example is that when you have an industry that gets more and more tertiarized, with the share of industry that decreases over time and the share of services that increases over time, you have an energy intensity that reduces because of that. That doesn't necessarily mean that there's been improvements in terms of energy efficiency. So now that this has been said, if you look at historically how energy intensity has declined, we get more or less minus 10%. I think it's minus 1.7% between 2010 and 2023, which, the figure can change a little bit depending on whether or not you take into account GDP at power purchasing parity or not. But what we're seeing here is that this decrease has actually been lower lately since the Paris Agreement. So not only do we need a shift, but we've actually gone the opposite direction in the recent years. If you look at different regions, you see, for example, that China has seen energy intensity since the early 2010s reduced quite significantly, but it's actually been very stale since 2016. Like we're at minus 1% per year since 2016. There is no, if you look at other countries, there is no apparent trend shift. So we're really not on a trend of improving significantly energy intensity, contrary to what we're trying to do here with this pledge. The idea is that there's going to be a lot of very disruptive energy efficient options and technologies that have not yet been fully rolled out, like such as electric vehicles, heat pumps, buildings insulation, and that sort of things, that are going to play a key role to introduce like the shift that we need in the next years. But this seems quite ambitious when we see the historical trends. Now let's look a little bit with at the different sectors with a few key examples. If we look at energy intensity of manufacturing industry we have 3 different cases here: China, the US, and the EU. Well, first of all, and we're not seeing here in the graph, but energy intensity went down between 2015 and now by around minus 16%. So that's pretty positive. If you look at China, this has been reduced quite significantly since the early 2010s. And this is mostly due to, especially if you look at the different dynamics with developed economies, if you have an industrial sector that is developing, you basically have more up-to-date new processes, best available technologies, basically. So you make a lot of progresses, whereas if you have an industrial sector that is stagnating, you don't have the same rate of renewal of technologies, and therefore the energy intensity doesn't decrease at the same rate. So therefore, in developed economies, this has not been very significant. Now, what I wanted to highlight is that if you take into account, so the activity that is used here to calculate the energy intensity is, industrial output, but that doesn't take into account the fact that the industry can shift from more energy intensive sectors, branches, towards less energy intensive branches. If you take that into account, you have the dotted line, or the lines that you can see here. And what we're seeing is that since 2016, most of the improvement in energy intensity in China is due to the fact that the share of energy intensive sectors has reduced. Actually, it's been quite stable since 2016, if you take that into account. In Europe, you can also see that, and mostly due to the energy crisis, that since 2021, the decrease that you see in energy intensity is also explained by the fact that a lot of the more energy intensive activities, as a reaction to very high energy prices, have basically left Europe for been offshore to other parts of the world, and therefore the activity has been less energy intensive, and it's not due to energy efficiency. Now, let's look at transport, and I have the graph is one very specific example, but first, we all know that EVs have had a spectacular rise in the last few years. So basically BEV, so battery electric vehicles, have been multiplied by 40 since 2015. If you look at both battery electric vehicles and plug-in hybrids, they've reached 20% of car sales globally in 2023, so that's quite impressive. But the fact is that they've not been very impactful overall. The share of EVs, despite reaching 20% of car sales, is only 3.2% in terms of stock. in 2023. And if you look at the transport sector as a whole, the share of electricity in transport is only 1.4%, sorry, of energy consumption, versus versus 0.9% in 2015. So that's not a very significant increase if you look at it this way. And in the meantime, traffic continues to increase, right? So passenger traffic has basically rebounded to its pre-COVID level, and goods transportation has continued to increase over time. Now, if you look at the graph, this is energy consumption from cars in the EU, right? So it's a very specific example. And we have here a BAU, right? So nothing really changes. We have consumption basically being relatively flat, increasing at a very small rate. Now, if we get to EVs reaching around 20% of the car stock by 2030, we reduce energy consumption by 11%. Now, this is very simplistic, but if you use measures that directly affect activity rather than just putting everything on technologies and EVs, if you reduce traffic by 20%, you reduce energy consumption, all of the things being equal, by 20%. Another example is if you increase the occupancy rate, so the number of people basically, or the tonnage of freight trucks by 20%, you reduce energy consumption by 20%. Meaning that at least we need to also consider measures that tackle activity and not just technology-based measures, because they could be more productive. Now, finally, let's look at energy intensity in households. So this is basically residential energy consumption per capita that we see again in different countries on the graph. So the global energy intensity has been relatively stable. So the idea is that there's been an economic development, especially in developing economies, obviously. So a higher access to energy services, but that's been compensated at least partly by energy efficiency. So in China, this has increased quite substantially, over 4% per year on average since 2010. But we can see here in terms of value of gigajoules per capita that it's very, very far from OECD countries. So the idea that if you look at the typical Chinese consumer, the energy consumption is much, much lower than the average European, and even more so the average American consumer. Another thing is the other line is supposed to represent, so we've had structural effects in industry. This is climate effects that have been compensated. So just to look at, for example, in Europe, the decrease that you see in energy intensity since 2021 is mostly explained by the climate and the fact that winters have been a little bit milder than on average. Oh, a little bit too fast here. Yeah, no, sorry. So now, so we've looked at historical trends. At Enerdata, we're also producing long-term energy scenarios, which I'm going to present. So let's look at how these objectives specifically compare to these long-term decarbonization pathways that we are producing. So first of all, a few words on Future. So this is the work that we do every year, that we update every year, where we produce 3 energy and climate scenarios up to 2050. So global scenarios, where we basically differentiate to have a range, of potential possible pathways for the future. We differentiate by, the level of ambition in terms of, the level of climate ambition, basically. So the first scenario being Enerbase, which is basically a continuation of existing policies and trends, and no particular additional measures that are taken. Enerblue is a scenario that basically includes the achievement of NDCs that have been submitted up to the end of 2023. So we get to basically a temperature increase that we estimate around 2 and 2.5 degrees by 2100. And Energreen, which is a more ambitious scenario that actually directly includes the achievement of the Paris Agreement and not just the NDCs. And that would lead to, we can't really have a clear statement on this, but a temperature that we think would be well below 2 degrees Celsius. Future is based on the poles model, which is a very partial equilibrium model that is very complete and comprehensive, and that covers the global energy system split between 66 countries and regions. And that covers basically all energy and use sectors, energy supply, and prices and GHG emissions related to the energy sector and the industry. So just again, to have an idea, an overview of what are the main results for the different scenarios, you can see that, so the gray line being Ener-based, so the less ambitious scenario, the Ener-blue scenario in blue, which is the NDC compatible scenario, and Ener-green, which is the well below 2-degree scenario. So you can see that they're very differentiated. I'm not going to spend too much time on this slide specifically, but they are very much differentiated in terms of evolution of consumption, share of fossils in the energy mix, and the evolution of CO2 emissions over time. So again, you will get the slides if you want to dig in a little bit more into this analysis. We also have specific content and webinars on in the future. So now that we've presented these scenarios, let's look at how they compare to the objective of first tripling renewable capacity and then the objective to double the pace at which energy intensity decreases. So what you can see here is that Ener-green is actually very close to the 11 terawatt objective in 2030, or another way of putting it is that we reached this objective in Ener-green around 2031, so with an additional year. So this is very much compatible, and vice versa, right? Ener-green is compatible with the objective. This also means that the objective is consistent with a deep decarbonization scenario that would lead to temperature increasing well below 2 degrees. On the other hand, if you look at Ener-blue, which is supposed to integrate the NDCs, we are very far from achieving the objective. I think we had around, I don't know, maybe 6 or 7 terawatts by 2030, and that we reach the objective only in 2034. So what it means is that this objective, this pledge, is actually more ambitious than the nationally determined contributions. A quick word on what it means to have this much investment in renewables, because that's something that's talked a lot. So we had a look at, in terms of system costs, what the Ener-green scenario compared to the Ener-blue scenario would mean. Ener-blue being already a scenario with a lot of renewable capacity that's being deployed by 2030 and beyond. So what we see is that indeed we are going to have a massive investment in the short term in the Ener-green scenario, and then over time you will have this additional investment that will pay off in the longer term and partly compensate for the additional investment in the short term. But this is something to keep in mind when looking at the objective, is that to get to this 11 terawatt objective by 2030, this massive investment that is required. Now let's look a little bit more quickly at how the energy efficiency objective compares to our scenario. Again, Ener-green is very close to the -4%, or actually includes a -4% basically decrease in energy intensity between 2023 and 2030. So very close to the COP28 pledge. But again, Ener-blue, the NDC scenario, falls short of that objective. So the conclusion is the same. There's a major shift, and NDCs apparently, at least this is our conclusion, are not sufficient to get to the COP28 pledge, whether it is for renewables or for energy efficiency. A quick word on our scenarios and the level of transformation that we need, and the fact that it goes beyond just emitting a pledge on just renewable capacity and energy efficiency. So in the Ener-green scenario, basically, the final energy demand in Ener-green compared to Ener-based is reduced by 31% due to energy efficiency gains, but also due to behavior and what we call energy sufficiency, right? A change in the way we consume energy services. Electrification needs to improve very rapidly. We get to, as an example of specific technologies, we get to 71% of electric cars in the fleet by 2030, and 47% of heat pumps in space heating. In terms of clean energy supply, we need to have in Ener-green, again, 95% of electricity that is CO2 free, the rest being potentially compensated, but at a very small scale by carbon capture, for example. And if you look at hydrogen, 94% of hydrogen needs to be from carbon-free technologies such as electrolysis.
So Quentin, if I may, this is just, you're looking at this slide, this is just huge. Because if we take a look at H2 only, 94% of H2 from electrolysis is just the reverse of the case today, because unless I'm mistaken, today pretty much 95% of hydrogen made out of fossil fuels, right?
Yeah, definitely. But yeah, I mean, the challenge is different. It's going to be H2 overall, it's going to multiply by a lot from what we have right now, where it's mostly industry uses, to H2 being maybe a significant part of certain energy sectors.
That's right. That's what is more or less planned.
Yeah.
Anyway.
Yeah, so I mean, we were one slide short of concluding anyway. So just to conclude of what's been said overall on the COP28 pledge. So definitely this objective is ambitious. It would be a major disruption of what we've observed historically. We would need a very important support of renewable energy and a massive rollout of technology and options that reduce energy intensity, that are really disruptive in terms of energy efficiency, as I mentioned, electric vehicles, heat pumps, etc. So this requires a lot of investment, and we're not really seeing that at the moment. What we've said in the last slide is that the COP28 pledge is compatible with a well below 2-degree trajectory. So it's an ambitious objective, and it's more ambitious than what we currently have in the NDCs. Now, one thing that we want to highlight is that these objectives are not sufficient in themselves to meaningfully tackle climate change. So historically, even though it's been at a lower rate, energy efficiency has improved, but it's not compensated the increase in activity. Energy demand continued to rise because you can have higher energy efficiency, but if the activity, the industrial production, the distance traveled in transportation, the amount of energy services in households increases, then energy demand is going to continue to rise. So more or less the same thing can be said about renewables, that we've had more and more renewables, but they've not substantially replaced fossil fuels. So if we just add renewables, but we have electricity demand that continues to rise, then it's not really going to do anything in terms of emissions. Plus, and the last point I think is important, if we only have strategies that are focused only on technologies, we are missing something that is quite important, and that's among other things, but I think one aspect that is crucial, the impact that it's going to have on materials, on metals, on critical materials specifically. So the conclusion for us is that these objectives are ambitious, but an actually consistent decarbonization pathway must also address somehow activity, whether it is through energy sufficiency, circularity, modal shifts, behaviors in general. We need to basically relieve the pressure on technologies, because these technologies, they are very uncertain and they are bound by limited resources. All right, so that's all for me. Maybe I can leave you the floor.
Yes. First of all, Geraldine and Quentin, congratulations for the timekeeping. It has just lasted an hour. So yeah, that's quite of an achievement because there's lots of insights to go through. So yes, we have a few remaining minutes for Q&As. So there's a few questions here. The first one is, where do you get the input data and how do you update it? So the answer, this one I can answer maybe. We have developed our own database named Global Energy and CO2 Database that, firstly was developed for our own uses and that we use to feed our models. So the whole idea was to have the best possible annual database in terms of the updates. So what we do is we use hundreds of sources, like the usual suspects in sources like, the UN or the OPEC and all those transversal sources. And on top of that, we scrutinize the statistical governmental bodies in each and every country. And, every time they release their own statistics, we pump it into a database and process it statistically, make the checks and all that thing. To have a full team here of a dozen people doing only that. So the name of the database again is Global Energy and CO2 Database. There's another question. Understanding that there are very limited data available at this point, would it be possible to comment on which trends you're observing for 2024? Many thanks. So yeah, that's right. We've taken a look at 2023 and then the projections to 2030, but not the trends in early 2024. The reason is that for this, you do need statistics. We do have a monthly database named NM Monthly. So we would need to, actually shuffle the numbers and come up with an analysis. But it's a good point. I think, Quentin, it's on our roadmap to do that at some point, right? Unless I'm mistaken.
Yeah, it is. But obviously at this point, it's still very early in terms of data that is available on a monthly basis, and you have to account for seasonality of certain indicators. So yeah, I wouldn't want to make a forecast for 2024, but it's definitely something that we will try to do by the end of the year, basically try to anticipate what's going to happen.
Yeah. Okay, and there's several questions about the same same issue in terms of how is it even remotely possible to reach those targets, considering the rise of population in developing countries and resulting into and the rise of GDP resulting into the rise of energy consumption and emissions. What's your opinion on that, Quentin?
So maybe I can let Géraldine say a few words, especially on the role of emerging countries as we've seen it and what's to expect in the coming years, and then I can maybe give the more longer term idea.
Yeah, so in the analysis, we're focused on China, India, and Indonesia. So China and India are the two largest populated countries in the world. They're emerging countries, well, with very strong development and still high development needs. So we think that we don't have precise figures, or maybe we have estimations for the population growth, but they should continue to consume more and more energy, just to improve energy access, to develop and to continue reaching a more development oriented way. I don't know what to say, but I don't know how energy consumption could slow down in those countries, or how they could consume less coal, for example, because there are many resources, more and more population, more and more energy needs and industrialization needs. So I don't know how to forecast, but I don't think it will slow down in the coming years. So it's bad news for emissions, because their energy mix are very coal intensive, but maybe we should do, that's the question for the COPs that we have seen, the need for financing to improve the development of renewables or to decarbonize industry. So yeah, that's it.
Yeah, no, completely. And if you look at, and I'm going to try to be careful with my words because it's a tricky topic. But if you look at energy long-term scenarios such as Energy Future, it's very clear that the biggest share of the burden to decarbonize is on emerging countries, and that doesn't mean that they have to do more in relative terms. It just means that they have activity growing, which is not the case for developed economies by definition. Population growing also at a higher rate. Therefore, this is where the future emissions will lie, actually, and this is what we need to decarbonize. So this is what makes all the negotiations very, very tricky. I mean, if you look at, for example, and to give a little bit of a more optimistic perspective, if you look at a country like India, which is key, or even if you look at China, where there's been a shift, right? There's still coal consumption that's been increasing, but there's definitely a shift towards renewable. So let's see if that continues and to what extent. But if you look at a country like India, I think it's an interesting example because they have this objective. So assuming that they achieve it, they have this objective of being energy independent, right? That's very important to them. So they have to reconcile their development with the fact that they need to rely on less and less on importation of energy primary resources. The problem is that they don't have a lot of energy resources. So that means that they're going to have to shift towards renewables, towards optimizing the relationship between their development and economic activity, industrial activity, and energy consumption. So I think it's going to be a very interesting example, provided that they stick to this energy independence objective.
All right. Oh, thanks. Speaking about scenarios, there's a question about the scenarios, and especially the IPCC scenario. How do your scenarios compare with the IPCC scenario, estimating that the remaining carbon budget to hit the -2 degrees target as approximately 1,000 gigatons of GHG? So how do we compare? So maybe I can answer part of this because it's kind of a recurring question. So we are currently at Anodata putting together a new service, benchmarking all main scenarios, main available scenarios. There's the IPCC, there's the IEA, there's all the scenarios that are being issued every year, like BP's, etc. So we are working on that, and probably I think in a couple of weeks' time, we're going to be launching this scenario benchmark service. But I don't know if Quentin, you have another insights on this subject.
Yeah, no, I mean, for us, we rely on these scenarios more than anything. I think this is more of an input, especially in the Energreen scenario. So what we're building a scenario, this is what we call backcasting, right? We're building a scenario around these constraints, basically, and to see what do we need to shift, what do we need to change in the energy system, what is a consistent pathway to reach these objectives, whether it is in terms of objective in terms of actual emissions per year, or a carbon budget that is, and actually in the Energreen scenario, it's based on a carbon budget that is, I guess, approximately that. I don't have the exact figures in mind.
Mm-hmm. All right. So in that case, IPCC is more an input, whereas the other scenarios that I mentioned are more comparable to ours, and this is where our benchmark will be focusing on, right? All right, thanks. Yeah, there's a question about sufficiency. Yeah, stating that, well, first of all, about the wording, some other institutes call it behavioral changes as opposed to sufficiency. And also it's kind of a luxury to talk about sufficiency efforts because in most countries the primary concern is access to energy. So how to change that? This is the question.
Yeah, I don't know. I can give my thoughts, even personal thoughts on it, but I do think it's key, and this is what we're trying to express. So first of all, how to change that? Well, you do webinars where you insist on the importance of sufficiency. To our scale, this is mostly what we can do. Improve also the metrics that are used, because it's the problem with sufficiency. It's quite hard to quantify especially in currently existing models. So I think we need to work a lot on that. So be more transparent in the way we measure and what we mean by sufficiency and what it means concretely. But I think, as you pointed out, I do believe in sufficiency as a virtue that we need to promote. I do think that the wording can be problematic, especially for countries that are developing, that see their level of comfort increase over time, and to ask them to compromise on that, it's a little bit more difficult. There are also countries, like the US, where the idea of politically diminishing the level of comfort is, and I'm not saying that's actually what sufficiency means, but that could be interpreted that way. So I think it's why people talk about behaviors in general more than sufficiency in certain cases, right? So optimizing basically behaviors to reduce energy consumption rather than promoting something that can be misinterpreted. But I think my first answer is how I see it, is that we need to work a lot on measuring it, defining metrics, and insisting on the importance of I mentioned the role of the impact that it could have, the scenarios that are not integrating sufficiency in a reduction in activity. There is a real problem with the critical materials that we need to address. If we can quantify that very clearly, then it's going to be obvious that we need to do something about it and not just rely on technologies.
Okay, thanks. So there's a question of about intermittent generation, which is also a recurring question. Given the enormous growth of intermittent generation, especially in China with wind onshore and PV, how does the country cope with system stability and flexibility needs? Is this mainly covered by the similarly growing conventional fleet or also by other means? And to which extent, for instance, BESS?
I mean, the rest of the fleet is not similarly growing, right? Renewables are growing faster. But I think it's mostly about at some point reaching maybe a critical point where it matters. But for now, they have so much thermal fossil-based generation capacity that it's not really that big of a problem at least at the country scale. Maybe there are some regions where there are congestions and system balance issues. But yeah, I think this is the case for a lot of countries. This is an issue that's going to be that's going to need to be addressed. But I don't think for China this is that much of a problem on a national level because they still have a lot of thermal generation capacity.
Okay, and one last question maybe because time is running out, and for everyone to know, if there's pending questions, we will answer by email. Right. The last question about the transportation. Considering what was said on Chinese and US increase in road transportation, fuel consumption and emissions, how do you perceive transportation emissions future trajectory of electromobility advancement isn't as fast or doesn't have as much impact as needed? Well, I think the question could be applied to Europe as well.
I mean, we could have figures specifically from our scenarios because they have different levels of development for EV. So we could have a look at them. But basically, yeah, what I'm pointing at is that this hasn't had an effect, EVs, for instance, in transportation so far, because it's still a very low scale of development, all things considered. It's still, what, 3% of the car stock, but it's definitely going to have a huge impact. I mean, provided that electricity generation is also decarbonized, but this both allows to decarbonize transportation fuel, energy from transport, but it also includes huge energy efficiency gains because electric vehicles are much more efficient than ICEs, right? So yeah, the deployment of EVs that we have in deep decarbonization pathways is very, very significant, up to almost most of the car stock, and this is going to have a huge impact on emissions for sure.
All right, thanks. So I think that's a wrap at this point. So thanks, Geraldine. Thanks, Quentin, for the insightful presentations, and thanks everyone for your attention. So as Quentin mentioned, you will be receiving the presentation document by tomorrow in PDF format by email. So check your email inbox, and that's about it. I wish you all very good day / afternoon / evening, depending where you've been attending this webinar, and see you next time then.
Thank you very much for attending.
Thank you very much. Bye.